Welcome back. In this segment, we're going to look at several combinatorial proofs. As a first example, let's assume that n is a positive integer. And let's prove that n cubed is equal to n minus 1 cubed plus 3 times n minus 1 squared plus 3 times n minus 1 plus 1. So this is a theorem of the form A equals B, and we want to write a combinatorial proof, which means we must find a set whose number of elements is equal to either A or B. Now in this case, A is much simpler, so let's focus on n cubed first. So n cubed, of course, is equal to n times n times n. That brings about the idea of applying the product rule. So if we apply the product rule, that means we could be counting the total number of ways to achieve a task when a task can be decomposed into 3 steps, each of which can be completed in n different ways. So to come up with a combinatorial or a counting problem, let's think of a set whose elements could be built in 3 steps, where each step has n possible options. Well, we could be building, for example, strings of 3 characters, where each character is chosen from an alphabet or a set of symbols of size n. So n cubed then is the number of 3-character long strings over an alphabet of n symbols. Now remember, this should become pretty straightforward at this point. Let's say you want to build a 3-character long string, and we can choose for each character a symbol out of an alphabet or a set of n characters. So we have n choices for the first position, n choices for the second, n choices for the third position, assuming we can repeat the symbols or the characters in the string. Then the total number of strings of this type is equal to n times n times n. So in conclusion now, we've chosen a set that is the set of all these strings whose number of elements is equal to, obviously, n cubed. Now to complete the combinatorial proof, we must find another way to compute the number of elements in the same set. And that way should lead us to this expression, which is quite complicated. So for now, let's focus our attention on the first term, which is n minus 1 cubed. Well, we can follow a reasoning similar to the one we just followed for n cubed, and realize that this number is nothing but n minus 1 times n minus 1 times n minus 1. How would we reach this number if we were counting the set of strings of length 3? Well, that would mean for each character or for each position in the string, we would be limited to n minus 1 characters instead of n, like in this case. So one way to reach that point is just to start with the same set or alphabet of characters as before and remove one element of that alphabet. Let's call that element S. What I'm talking about here is this number could be the set of all the strings of length 3 taken from the set or the same alphabet as before, with the extra constraints that you are not allowed to use the particular symbol S. So if you have an alphabet with n symbols, you remove one of them called S, you're left with n minus 1 characters to choose from. And so this number now is the number of 3-character strings that are built over the same alphabet, except you're not allowed to use the character S, which is any chosen character in the alphabet. Now, of course, these two numbers cannot be equal because here we're counting all of the possible strings of length 3 over the alphabet, where here we're counting all the possible strings of length 3 over the alphabet, except the character S. So for these two numbers to be equal, we must add all the strings that do contain S. So let's say we're counting the strings now that contain exactly one occurrence of the symbol S. Well, this occurrence must appear in one of the three positions. So we have three choices for positioning the character S. And then for each one of these positions, we have two, say these two open positions in which we can position then any one of the other n-1 characters. So we have n-1 options for this one, n-1 options for this one. We multiply those two to get n-1 squared. And then let's not forget to multiply by 3 because initially we had 3 options to position the S, either here, here, or there. So this turns out to be the product of 3 times n-1 times n-1. And as we just explained, that's the same as the number of strings over the same alphabet that contain exactly one S. Now, of course, we also need to count the strings that contain exactly 2 S's. So how many ways do we have to position 2 S's among these 3 positions? Well, counting this number of ways is exactly the same as counting the number of ways to position one character that's not an S. And we have 3 options for that. Once we pick the position that does not contain an S, then the other 2 positions that do contain an S are determined. So there are 3 ways to choose the 2 positions that contain an S, and then we have 1 position left. And for that position, we have n-1 options. Therefore, the total number of strings that contain exactly 2 occurrences of the symbol or character S is this number, 3 times n-1. Finally, we must count all of the strings of length 3 that contain 3 occurrences of S. Well, of course, there's only one choice, and that accounts for this 1. So in conclusion here, these 2 expressions are equal because there are 2 different ways of counting all the strings of length 3 over a particular alphabet. Here we have the direct computation, and that number must be equal to the total number of strings of length 3 that contain 0S, the number of strings of length 3 that contain exactly 1S, the number of strings of length 3 that contain exactly 2 S's, and the number of strings of length 3 that contain exactly 3 S's. Having covered all of the possibilities, we have therefore counted all of the strings of length 3 over the same alphabet, and therefore these 2 numbers must be equal. For our next example, let's prove the following theorem. Assume n is a positive integer. Then the sum for I equals 0 to n of n choose I is equal to 2 to the power n. Now remember that this notation here, which is read n choose I, is just the same as C n comma I. So why don't you pause the video and write a combinatorial proof of this theorem, and then come back to check your answer against mine. Okay, so here is my reasoning. Remember, we're trying to find a counting problem. That is, we're trying to find a set whose number of elements is clearly equal to one of these 2 expressions. If you don't know how to start, I always advise you to go back to the definitions. So for example, what's the definition of this term here, n choose I, or C n comma I? Remember that by definition is the number of subsets of size I of a set of size n. So right there, this should make you think about using a set of size n. Now, why is that a good idea? Because if you have a set of size n, then this number right here should jump at you. If you remember the basics of set theory that we discussed earlier in the course. If you have a set of size n, then 2 to the n is what? It's the size of a set, which is That's right, this is the size of the power set of the set of size n. So in other words, this is the number of subsets of a set of size n. So now all we have to do is to prove that this expression here is just another way of counting the number of subsets of a set of size n. Well, another way to count the total number of subsets of a set of size n is to partition or group these subsets into different categories. So first, you have the subsets of size 0. Then you have the subsets of size 1, and then those of size 2, etc., all the way up to the subsets of size n. Well, notice, when I is equal to 0, n choose 0 is actually the number of subset of size 0. When I equals 1, this expression is the number of subset of size 1, and so on and so forth until I is equal to n, which is n choose n is the number of subset of size n. So this is exactly the expression that we were looking for. This is the sum of all the numbers of subsets of a given size from the size I equals 0 all the way to size equal n. Since all of the subsets must be in one of these categories, the sum of these numbers must be equal to the total number of subsets of that original set. So this is one easy way to write a combinatorial proof for this theorem.